everyone. Hope you're doing well. Thank you so much for joining this talk. I have been able to attend few of the prior sessions of the festival, and I personally think those are really brilliant. I hope you too could find some time to be part of the sessions, and of course, that you find this particular one interesting. I am Anushree, like they've said. I've been part of dunnhumby for close to 5 years now as a data scientist, of course. And I'm going to talk about just exactly the title that you're seeing on your screen, which is stockpiler identification using isolation forests. Um, Now, why was there a need to identify stockpilers and why did we choose this particular algorithm to solve for it is something we're going to focus upon in this talk. But before that, something about myself. I have a master's degree in economics from the University of Mumbai, India. Post that, I pursued actuarial sciences for around 2 years from the Institute and Faculty of Actuaries UK. And alongside, I did work as an actuarial pricing analyst for almost a year in one of India's leading insurance companies. And it was all good. But then I realized I do like experimenting with techniques, being innovative, and hence I decided to move to the field of data science instead. That's when I joined dunnhumby in 2017, and I've been here since then. Um, I have been able to work across a breadth of solutions, apply multiple statistical ML techniques to solve for business problems, like the ones that you see on your screen. For example, what's the optimal frequency that items or categories should be promoted at by transforming the entire context to a banded setting. Stuff like understanding potential of multi-buys by using NLP in the product descriptions, and then trying to figure out the future need or importance of products in the next COVID wave, using Nielsen statistical rules. So these are a few of the projects that I'm really, really proud of, apart from the one that we're going to discuss today. I am highly inclined towards Bayesian inference and currently trying to find its potential use cases in retail. And lastly, I do write on Medium, yes, and I'm also part of Nerd for Tech, a technology-driven educational media house. So as you see, I do have an inclination towards putting myself through the uncertainty of data and algorithms. So what I'm going to share with you is one such instance of delayering the uncertainty in customer behavior that all of us kind of experienced together due to the pandemic. And so I'm going to ask us to kind of do a flashback now and go back to the time when the pandemic initially hit us. I know it was a really hard time for all of us, and I think we've all been, though quite shaken, but strong too about everything that's happened all across the world and the pandemic, the way the pandemic came onto us. But one thing was quite common across countries, and that is what is being reflected by the top chart that you see. We took it from a public website pertaining to the use cases. Now, what this graph is simply showing is the number of weekly cases, and it's trend starting March 1st week till April last week, so around 8 weeks of period in 2020. So this is the same time around which we were really fighting this disease for the first time in history. This was the first hit of the pandemic, and hence how all of this uncertainty got reflected in our daily grocery demands and visits to our favorite stores is something that is highlighted just below this chart. Now this chart, the bottom one, shows an example of the average number of units that customers bought in each visit of theirs to a specific US retailer over the week starting January until April end. And you will see around the same time for which we looked at the top chart when the pandemic hit us, that very time the quantity bought by customers in their visits kind of suddenly picked up and in a way which had never been seen before. So you notice that the first 8 weeks of 2020 in the bottom chart kind of followed this one constant trend, while the first week of March, which is week 9 in the chart, there's this sudden peak which seems to have had continued for a couple of months. And if you think of it, this kind of made sense. We were really concerned about our loved ones here. And hence we wanted to minimize any chance of stepping out. Whatever essentials we needed that couldn't reach our homes, we wanted to minimize our visits to grocery stores and try and pick up as much as we can on that one visit. And that is what was happening during those days. I think everyone remembers that time as the stockpiling days all across the world. Now, where does dunnhumby fit in all of this? dunnhumby is the world's leading customer data science company. We unlock the value of customer data, create engaging experiences that put the customer first, and that makes us help retailers and brands perfect the entire science of shopping. Um, we collect, we analyze, we also utilize huge quantities of data to drive outcomes for our retailers. But the question is, how did we really manage to do the same during such an unusual period where the data that we were seeing had totally exploded to proportions that were really, really hard to measure and evaluate? We stepped up. We helped retailers solve their availability issues. We equipped them with sales demand forecasts. We guided them with full-fledged data science solutions at lightning speed to help them quickly adapt to the changing environment, and also drove the attention back to what lies at the center of dunnhumby's heart, which is customers. Um, we wanted them to be served well, even better during the pandemic. And that's when we went forward and suggested we must identify stockpilers. A lot of our clients were really interested in knowing who are these customers who are changing their behavior so drastically. How are they changing it? What are they doing differently? Because identifying such customers and their trends can lead to further actions related to specific regions, certain kind of families that these stockpilers might have belonged to, and also understanding if these are one-time stockpilers, seasonal stockpilers, or perpetual ones. Understanding these dynamics, really identifying such behavior was very, very crucial. And hence, we thought it's a good time to look at the data. We're data scientists. That's the first thing we do. We saw 3 top-line insights come out of our initial analysis, just like you see on the screen. We saw that most of the customers were stocking up higher quantities of items in one single visit. But there were these customers too who were also shopping across really wide variety of categories, which also made sense given that suddenly everyone started cooking and creating stuff at home. And then there was this third group of customers who were stockpiling, yes, and not only higher quantities, but across a breadth of categories as well. So a mix of 1 and 2 that you see here. That said, they were doing this way more than others and quite unusually. And that became our business problem to solve. These were the set of customers we wanted to understand more, apart from every other customers, of course, in order to not miss out on reaching out to even a single person during the pandemic. That said, there was a lot of brainstorming that was done to decide as to which algorithm could give us this target group. We knew a clustering technique will definitely be able to give us different groups of customers, but given the environment and the data that we were dealing with, it would also fail to differentiate between highly atypical and normal customers. And we, of course, did not want that. On the other hand, if we looked at the extreme stockpilers as anomalies instead, owing to the fact that only a certain percentage of customers were behaving more unusually as compared to others, using an anomaly detection technique, though will just give us 2 groups, yet it will be successful in detecting extreme behavior, which we actually wanted to identify. And hence, we chose this path. So how are we going to explore the technique and the problem statement itself? We will start by discussing what anomaly detection is, move on to the entire foundation of trees and forests, and how isolation forests are built on top of those. Once we're confident about the algorithm, we will move on to our business problem of identifying stockpilers, look at the results together, see how isolation forests fared. We will also look at a simple a very, very simple snapshot of from where you can import the model or the library and how you can use it to predict your anomalous data points using scikit-learn on Python. So without further delay, let's start with some context around anomaly detection. Okay, so another general term for anomalies is outliers, which is more commonly used. And the way we think of it generally is something that is unusual, something that deviates from the normal, something that is different or even few in number. Now, it does have wide applications across different industries. Examples could be an intrusion network data, a fraudulent payment in sales or credit card business, a breakdown of piece machinery, even in the health industry, a sudden pathological status in medicine. These are all examples of unknown and often undesirable events. These are all deviations from the normal behavior. And the fact is, because it has these innumerable applications, anomaly detection is usually ill-defined. So what anomalies are exactly? But one of the ways that it's usually approached is when you try to map your feature space into a one-dimensional anomaly score. And the next step is to have a very, very easy model that turns this anomaly score into kind of classifier where you say, this is considered to be anomalous or not. Now, this can have different flavors. Preferably, you would do a supervised one, but oftentimes it would be difficult where you don't have good examples of anomalies. So many times it's unsupervised and you quickly get into a territory where you land up using business logic or domain logic. For example, you might know with your experience that it's usual to have 0.2% of your data as having anomalies. In that sense, it's a little murky. Or in other words, this is a kind of a gray area when we work with anomalies. Like I said, there's just a lot of flavor of how your data can look like, how your problem statement can look like. So here you have a bunch of training samples. And then at prediction time, you have data that is hopefully from the same distribution, but sometimes you can have anomalies. Now, this is what is called novelty detection, where you're interested in seeing if any patterns are changing from your training set to your prediction set. But this is different from outlier detection, wherein you can also have anomalies in your training set. And that's where isolation forest comes more handy as well. It works better in this case. So you have anomalies in your training set that are small in number, and isolation forest can help identify those easily. We will come to how it exactly does that, of course, but in that sense, you might feel it's similar to a classification problem. But like I said, most of the times it's not labeled and quite imbalanced too. Before we move on, one of the things to take away from all of this discussion about anomaly detection is that all of the current existing techniques have one thing in common in the way they approach anomaly detection, which is they profile normal instances first, and then they move on to identifying data points or instances that do not confirm with the identified normal instances. And sadly, what this leads to is, that is the consequence of profiling normal instances first is, there could be too many false alarms, that is having normal instances being identified as anomalies, or too few anomalies being detected at all. For example, it could be dangerous if a cyber breach isn't caught on time, right? So we will talk more about how iForest comes handy in such scenarios because of the way it's built. And hence, I think it's a good time for us to move on to trees. Talking of how iForests are built, we're going to start with understanding what trees are. Now, trees are very nice. They have a very intuitive approach. They have really nice expressive features. And because isolation forest is built on top of these trees, it's also a good choice for tabular data. So the concept of trees is that you are recursively splitting your training set or data set into parts. Usually you take one dimension and decide this is the value that I'm going to split it at, and then you basically repeat the process, but on a new data set or sample. After we've decided on the splits, and the splits are decided on, well, the task that you have at hand. If it's a classification problem, you are usually using some kind of impurity where you separate it as far as possible. And you need to have rules as to how am I going to stop splitting. There's this third component, which is now that we have a tree, how can we use that to say something? That's the most crucial component. Then what happens is once you have your sample, you follow the decision rules that came out, check at what node or bucket it ended up at, and then you know how to build a story out of it. So in this case, if it's a classification problem, say it starts from the top, goes to the left, then to the right. Historically, we've only seen blue, and that's where it's ended up. So we classify it as a blue sample. And that's why you see that little 100% there. The problem is, of course, that it's pretty rudimentary, has a very high variance, can overfit very quickly. So usually what you do then, you subsample your data both in the number of rows or examples and the number of features that you have, and you repeat the process a lot. You repeat, keep on repeating. The idea here is that you don't have a lot of bias here because you're just averaging out all of the results again and again and again. But the variance gets reduced because the overfitting will happen only with some of the trees or overfitting in a different way. But on an average, hopefully you will get a good score. A lot of more basic machine learning models do work like this. Some nice things about forests. They're interpretable, like we just saw. They're general. The rules that come out that are easy to interpret. Of course, for forests, that's not directly possible as opposed to trees, but it's still directional and something that you can explain as well easily to others. It's very scalable because you can parallelize it if you have a huge data set and you want to have a lot of trees, that's easily doable using forests. And it's very expressive in the sense that because you have this very basic decision rules, but then because you recurse it, you can learn very intricate nonlinear patterns as well. So now that we know the fundamentals of trees, how can we use these different components of trees to do anomaly detection? As I mentioned before, we're always interested in knowing some kind of value that says something about how anomalous is your data point or how normal it is. And that's what we're going to work towards using isolation forests. So for simplicity, I've taken one dimension for a start. These are numerical values. Now, visually, we can make out easily which one is the most or more anomalous one. And I'm hoping you'll say the extreme left data point here. So what your mind did was to look at this point that's sitting there on the left, quite lonely, just one single point there. Yeah. So if we think of it logically, we'd want the forest to use such factors like distance, density, etc., as notions to construct the anomaly score. So what we're going to do is we're going to take the minimum and the maximum value that we observed in this dimension. And this doesn't have to be on the entire or whole data set. This can be, in case of forests, you subsample your data already, but it can also be that we're lowering the tree where we already split part of our data. And we're just going to take a random point uniformly sampled. So we're going to keep oscillating between minimum, maximum point, and then we try picking up a point which is uniformly sampled. And say we split here. Because it's uniform, it's more likely that the split will happen in between these points that you see than between any of the points that you see on the right-hand side, right? So the effect of sampling uniformly, even though the data points aren't spaced out uniformly, is important for this algorithm. So we first split it into two. Now we've split it again. And what we're interested in seeing is how many splits does it take for a sample point to be isolated? And that's where the name comes from. So in this case, we split both sides again. And here, this point, our lonely point, has been isolated. So this point took two splits and then it was by itself. And we keep doing this. And our termination point is until everything is split or the data points are completely duplicate. Every time we make a new split, we just randomly sample a dimension, whether there's still information in there. So if there's just one dimension where there's only duplicate values that we don't sample, that one, so the left and the right side become independent of each other in the sense that they do not sample in the same way. Okay, so next what I have is something like this, where we have two dimensions. You can think of Q1 and Q2 being two different attributes. And say we want to isolate those points that are on the extreme right and at the bottom, just next to where it's written Q1. They seem like anomalies, yeah? So the first step, what we do is we sample for training a model. Just like how I mentioned for the one dimension example. Of course, depending on the data set, the sampling proportion can be different. The following step involves making a tree for the sample we drew from step one. So step one, we drew a sample. Step two, we're creating a tree for the sample we drew from step one. Now, this step involves two random elements, and these are the ones that you need to keep in your mind. A random choice of an attribute, that is either Q1 or Q2 in this case. B, a random choice of a Q1 or Q2 value between its minimum or maximum, that is. In this case, we've taken Q1 and we've split it using Q1 dash. Next, we need to repeat step two of creating a binary tree for the two sub data sets based on the binary split. Now, apart from the two parameters, I asked all of you to keep in mind of a random attribute and random value. Another feature of isolation forest, rather assumption that isolation forest works with, is that anomalies are few and they're different. Hence, fewer and different data points are isolated quicker, such as the data point at the very lower right corner. So in other words, it takes less path for them to be isolated. Doing this iteratively, we create a forest, which will be a collection of such trees. We repeat the process many times because that's how we get to a forest, of course. Again, with subsampling your data in both directions. And what we do then is when we have a new point, so we have a point and we want to know how anomalous is this point, we put it through all of these trees and we measure how many splits does it take for this point to be isolated. Now, the splits could also be called partitions required to isolate a point, and this is equivalent to the path length from the root node, which is the top node that you see, to the terminating node. And this is what the anomaly score is based on. I really haven't mentioned the formula here, but the idea is we have an anomaly score for each tree. We average them across different trees to get the final score of an entire forest for a given data point. The shorter the path, the closer the score is to 1 and more likelihood of it being flagged as an anomaly and vice versa. So for example, in this case, for this tree, the depth it goes to is 4. Here it's 3, here it's 3 again, and then it's 2. So all that you need to look at is the green bars that you see. Those are what will give you the depth itself. So 4, 3, 3, 2. So then we can say on an average, it took a path length of 3, and that's the notion behind anomaly detection using isolation forests. We can do this with all our samples, both in our training set, prediction set, and then we map this high dimensional data to a one-dimensional score of anomalies. Now, if we do that, of course, the way we constructed the isolation forest, the hope is points that are more anomalous are isolated more quickly, which then means if we plot them on a histogram, just the way you see on your screen, you get to see these points that are more anomalous, that are more on the left. This means now that we have this easier to reason about space, we can determine a threshold to say, okay, we consider everything below this value, above this value to be an anomaly. Of course, it's a lot easier to do if it's supervised, but usually we want to bias this as well, because in a lot of cases about anomalies, the loss or the cost of making a mistake one way or the other is very, very different. So in that sense, you'd rather have a false notification that you're having, say a cyber breach, than not know about it at all. So we decide on a threshold point, and now we basically have a classifier for where we can put new samples through all of these trees, and then calculate the anomaly score, and then determine whether we call it an anomaly or not. So that was everything about the algorithm, how it works, the intricacies of it, which I hope you found really simple and straightforward, given the fact that it's tree-based. What we're going to do next is quickly jump on to the next part of the talk, which is where and how did we really use this algorithm. I'm going to refresh our memory a bit. We had our environment of the pandemic, all of the confusion about the uncertain times, a lot of extreme behavior being seen everywhere. And we wanted to identify who are those customers who are behaving differently, anomalously as compared to the rest, so that not only can we keep a tap on them during those stressful, sensitive times, but even in the future. So now is the time to look at the data. So we knew extreme behavior was being seen in the months of March and April when the pandemic suddenly hit us. Like I said, it was our first. So those 2 months definitely became our focus period. Let's say we called it our post period. Now I will come to why it's a post period, but let's just say for now it is. Now that said, we also wanted to capture who are not confirming with the normal behavior. What I mean is, we know everyone was going through uncertainty in their heads. We know everyone was confused, but what we were interested in finding out was if the feeling of uncertainty was consistent or not. So instead of taking absolute numbers, we went back to 2019, the same months of March and April, took those as our baseline and found our change percentages from 2019 to 2020 for the months of March and April. So to summarize, that gives us one phase of metrics that we took, which is a change percentage from 2019 to 2020 for the months of March and April, which was our post period of 8 weeks. Now, since we had a post period, another aspect that kind of helped us capture distinction behavior from normal to the stockpiling days was considering a pre-period, which was January and February. So in the similar fashion, like we had a post-period change, now we had a pre-period change. So 8 weeks on either sides. And that's what you see being compared on the x-axis and the y-axis on these charts here. Now, these two charts, these are actually talking about two metrics that we consider to calculate the change percentages. So the first one is the average units that customers were picking up in each of their store visits. And the second one is the distinct count of categories being picked up in each visit. So now that we know the metrics we use, the two phases that we considered, let's try reading through these charts. Just to clarify, since we're looking at change percentages, the X and the Y axes both give percentages. And you will see this tiny box at the top saying into 100%. What this means is any value that you see on either of these axes, the true value is actually that into 100%. So if you see 10 on the X or the Y axis, that actually means it's 1000% and so on. So these are really huge numbers, or jumps rather, from 2019. But let's try understanding the relationships before we get on to what the model really gave us. Let's start with the first one. So this one is giving us a change in quantity per visit. And if you think about it, had there been no to a little change from 2019 if it was a normal year, all of these data points would have been clustered towards 0%, right? But we can see that wasn't the case. So definitely there was a lot happening in reality. Now, on top of that, if I show you what the average numbers look like during that time, it kind of looked like this. So you see, all of these data points seem way to spread out in all directions, away from the average itself. Now say we keep some buffer on either side of the average and try judging from the data what could be anomalous. You will see that there is this group on the left and somewhat between the values 0 and 10 or 1000% on the y-axis, where we see it starts getting a little sparser. And if we think fit, a change percentage of 1000% or even 500% seems huge in itself in the post period, in spite of the existence of the pandemic. So we definitely can expect something unusual going on there. On the other hand, if we look at the tail on the right, where the pre-period change seems abnormally high, so that's the period when the pandemic had not picked up as such, Seeing a huge percentage change there seems to be suspicious again. So that could be an anomalous region too. Now, looking at the second chart, which gives the category count change percentage, also seems to be showing similar behavior. And so it seems that if I have to call customers as normal, they should be falling somewhere here. And anything in the areas around it or at the extreme ends seem to be anomalous customers. Now, whether they were stockpilers or not, we will see that later. Next, of course, we ran the algorithm, and though it's tree-based, we aren't building any supervised classification or regression tree here. It is an unsupervised anomaly detection technique that we're dealing with, meaning we do not have any categorical, even continuous labels here to check the performance of the model by directly splitting the data into train, test, validation sets, etc. That said, we still decided to go ahead with training the algorithm on part of the data and seeing if we can carry forward the same anomaly scores generated from the train set to the test set. The first check that we did was more from a context point of view, and this is a plot of the average weekly quantity bought per visit by each group of customer identified by the algorithm on the test set. And we can see it did a really, really good job in separating the anomalous customers from the normal ones. Looking at the trends itself, wherein the difference between both sets of customers is really minimal in the pre-period. So you can see it was around 12 units per visit on an average for normal customers, while it was 11 for the normal ones. So not much difference. While in the post-period, if you look at the blue line, which represents the anomalous customers, shows a clear distinction behavior from the normal customers. The same numbers here are 22 and 16 units being bought per visit respectively. So the gap, the difference kind of widened in the post period between these two segments of customers, which is what we wanted to detect. Next, continuing from the earlier plots that we saw for our data and embedding the iForest results on top of the data, gave us something which we expected, which was, of course, a good sign again. So if you'd recall, we said the blue data points seemed more like customers who are similar to each other than customers are represented by the yellow data points that the algorithm identified as anomalous. Now, what we also discussed earlier was that these customers will seem to be having really explosive behavior in the post period, and hence the left-hand side of both metrics reflecting on huge post period changes, but there is this group on the right-hand side too that came out as anomalous by the algorithm. Now, when we deep dived, and I will give you a glimpse of what exactly we did, but when we did that, we found out that these customers, the left-hand side ones, were constant stockpilers, meaning they always, most of the times, even in normal times, have a tendency to stockpile from time to time. And these customers actually are infrequent customers who, though, have been quite consistently engaged with a retailer for a very long time, but this retailer wasn't their preferred retailer for their grocery shopping until 2020. Now, the important question was, were both of these groups the customers we were interested in? Were these indeed our stockpilers who changed their behavior or acted differently from other customers due to COVID? Or do we need to keep these two groups separated when deciding on the right actions to take? Now, to be able to do that, we're going to look at the next slide. So when it comes to interpreting the results of iForest, we can either just stick to classic approaches of looking at trends, just the way we did before, understanding average metrics of each group, comparing if it makes sense, and directly action upon the desired group. Or really efficient and nice approaches to carry out a real interpretation exercise. And the objective here should be, now that we have our anomalous customers, how should we understand why these customers were considered anomalous, right? And to do that, one of the approaches that we came up with was to train a surrogate decision tree. The purpose of this surrogate decision tree was to find records with the anomaly flag. And because it's a tree, in order to identify such anomalies, it will find segments of similar anomalies, discover how to separate them from records that are not anomalies. We can use this decision tree then to describe anomalous segments of the data. So just to summarize, I'm going to take an example of trees and forests only, like literally trees and forests. And say the green ones are normal customers, while the orange ones are the anomalous ones. We started with a data set where we did not have any labels at the start, and we really wanted to identify our anomalies. We ran our iForest algorithm, which helped us separate the different and the few customers from the normal customers. And then we got two groups of customers in our data where we could put labels that we got from the algorithm as anomalies or non-anomalies. So from an unsupervised problem, we transformed it to a supervised classification problem. And so lastly, we took the label data set, ran a surrogate decision tree on top of it to get what thresholds or rules were used by the iForest algorithm to separate the anomalies from the known anomalies. Simple. Yep. What you see on the left-hand side is the tree we got from our decision tree. I've just kept it to a depth of 2 for the purpose of giving you a visual picture, of course. You see the right-hand side of the tree is majorly the anomalous customers, the dark purple buckets that you see. This kind of contains 82% of the anomalous customers. So if we try reading what it says, the first distinct feature and the value that helped the algorithm identify the anomalous customers was the post-period change in number of categories bought in each visit, and the value was more than 431%. So a post-period metric came as significant feature to start with, so that's a good sign. Now we have another segment as well, which says a second feature that helped differentiate between anomalous, non-anomalous customers was again the change percentage in number of categories, but not in the post-period, but in the pre-period. And that's the second group that you see. Now, this might seem questionable, seeing that we only wanted to identify customers who were behaving unusually due to COVID. But the fact that this is a really small proportion of our anomalous customers, and like I mentioned earlier, after digging into it, we found that these were just infrequent ones who happened to increase their engagement in 2020. So not really stockpilers due to COVID, but yes, some different behavior from the usual set. So you see the left-hand side of the tree completely blurred because the right-hand side gives us our focus group. So running this surrogate tree did help us in understanding and deciding on what group to track. But in all of this, what's important is that such an interpretation exercise told us that A, more than the quantity being bought in each visit, the anomalous customers actually showed unusual behavior in the breadth of categories that they were engaging in, and B, that though there are these two groups of customers behaving anomalously, but they're doing it in their respective ways. And for our purpose, all we have to do is focus on the right set of customers. So what this majorly gives us is some decision rules that we can use to understand what really was happening, right? And hence, when we derived the rules from the tree, this is what we got. Two sets of customers. The first one was different majorly in their categories being bought per visit as compared to the other group. And then the first group had a further distinguishing feature we found when we looked further in the tree, which was the post-period units bought per visit. And so, since both of these trees were post-period metrics and their values were kind of showed really stark differences from the other group, using these told us that the first group was that of stockpilers, while the other one, the usual or rest of the customers. So you see how easy it was for us to really get these metrics, get our right set of customers, start proposing to the retailer how they can really track or profile them over time. Okay, so now we've done understanding iForests, hopefully, and we saw how we used it to identify our stockpilers. And now we're going to quickly kind of check a few things that are important when we're talking about isolation forests. It's not your usual tree, But nonetheless, there are three very important hyperparameters that you need to be mindful of while working with this algorithm. Like I said, it's not your usual tree, but it is a tree. So yes, the usual decisions about the number of trees or estimators that you'd like to use and the number of samples that you'd like to train on for each tree is something that you can play around with. Now, it's an unsupervised technique, so of course, we've got to see what values of these hyperparameters make the anomaly score converge, meaning what value should you use based on your data that will make your anomaly scores not change no matter how many times or how many iterations you repeat the process after that. So the original paper suggests that using 100 trees, 256 random samples per tree worked for the data and should work for most of the data. We somehow tried and tested and found out that while 256 samples kind of seem to be working fine, the number of trees or estimators needed to be increased to through 50 for our data, which kind of worked well even when we generalized it to a new data set. So all in all that I'm trying to say is do not miss out on these two values when working with this algorithm. That said, the third hyperparameter, something that is quite common to all of the anomaly detection technique, which is deciding on what percentage of the data points or customers, in our case, would be prefer being considered as anomalies. Now, I used prefer because we can tweak this, but the decision itself can be another exercise in itself. Normally, you choose a certain percentage and say, let's take top 10% as anomalous customers. And yes, you can do that. You can do that here as well. But what happens is that that 10% might not be all of your anomalous customers. That 10% might include non-anomalous customers on the other hand. I say this because as per the algorithm's implementation, especially on Python, the more negative a point, the more anomalous it can be considered. Also, when the data changes, just arbitrarily deciding on 10%, say, might work once, twice, but might not work so well if different kind of customers start coming in. So the second option is rather to decide on what range of the anomaly scores you'd like to be considered as anomalous. And that's because the moment your data changes and the resulting anomaly scores as well, all you have to do is based on some statistical rules that you decide on. You can decide on a range for your anomaly scores that you'd like to keep as anomalies, no matter what the data is. Of course, you can refine it over time, but it saves you from blindly following a percentage-based method, which might not work so well every time. Okay, so this is the final league. Here are a few steps to simply show you how you can go about importing the isolation forest model from sklearn.ensemble. Then you instantiate the model with your decided hyperparameters, your contamination percentage, fit the model to your training set using the fit method. Then you use the decision function method on your test set to get the anomaly scores, and the predict method to get the flagging based on your contamination percentage. Generally, when you work with any anomaly detection technique, -1 would mean it's an anomaly and 1 would mean it's non-anomalous as for the chosen technique. I generally have a habit of transforming it into ones and zeros for ease of interpretation instead. So you can do that too, but that's totally up to you, of course. You can do other stuff, and you must play around with the anomaly scores, which would be a more efficient approach. But the usual steps should look like this. Again, this is the most simplified version of the code of what you actually would be doing in reality. There will be 100 more steps before you actually get to this part, and there will be 100 more posters as well. But this should give you a flavor of what's available when it comes to using the algorithm. This is scikit-learn. There are other packages as well. H2O gives really beautiful functionalities to visualize the results in a simpler manner. But then there are other functionalities too. But both of these packages use a different logic for calculating the final anomaly scores as compared to the original paper, just to keep things simple. Hence, do go through that documentation if you're planning to use it. And that takes me to the last slide. Here are a few stuff that you can treat. I found this really helpful. There are these interesting blocks, then the scikit-learn H2O packages that you can explore. Also the original paper, that's the first one that you see, which you must go through. It's really well written, really well expressed and explained. I kind of did it back and forth at each step of my analysis with that paper. So yes, do give it a read. And lastly, very important, dunnhumby is hiring. We are always interested in fresh talent, new perspective, and are looking for bright data scientists all the time. So if you're interested, please get in touch with us. You can directly get in touch with Rob Rendell if you're looking for a role in London. If you're based in any other part of the world, like me, I'm sure he will still be able to guide you in the right direction. Thank you.
Perfect. Thank you, Anushree. I think, if I'm honest, I think you've missed your calling. I feel like you should have been a lecturer or a data science trainer. It was a really, really good session. Clearly very, very well thought out in terms of the content, and your presentation style. I absolutely loved it. So thank you very much for sharing. If you've enjoyed it at home, please do drop us a little message in the chat. It is nice. I can see there's been hundreds of you literally watching along. So yeah, it's nice to let Anushree know that she's been appreciated. As mentioned, we are going to take a few questions. So there is some questions already in the Q&A, so we will jump into those. I have a couple of my own as well, and we'll go from there. So thank you for sticking around for the questions, Anushree. Just in terms of some comments, it's always nice to get a bit of feedback, isn't it? So Manoj brilliantly explained, Anushree. Tara, brilliant session, thank you. Ting Ting has given us the clapping emoji, which is, it's not quite the same as a real round of applause, but it definitely all helps. We've also got Anthony, James, Matthias, Louis, Carla, Adam Hornsby, welcome along, Adam, Hayley Hubbard, Simran, Andrew, Michael, Jeffrey, Daniele. Honestly, the list goes on, and I will come back to some more of those and give people a shout out. But in terms of the Q&A, if you want to open the Q&A, Anushree, you'll be able to read along at the same time as I'm going through it. If any of it's been covered already, sometimes it's good to recap. Sometimes, we can follow up after, or sometimes we can skip past the questions. I'll kind of take your lead on that. In terms of that first question, then we'll jump into the first question there from Amir. It's had 4 upvotes. There's a couple of other people out there that are keen to chat about this one. So in terms of Amir's question there, how does identifying extreme behavior customers help in demand forecasting, since these extreme behaviors may not be good indicators of prediction? Have you got any thoughts on that one?
Yeah, I think so first, thank you so much for this question, Amir. I'm really feeling there's something that I might have explained not so properly. So these are 2 different objectives that we're talking about, 2 different questions that we're talking about. The scenario, if I take you back to the pandemic situation at that time, Amir and everyone, what we were doing at that time was to be able to help retailers in every possible way still be relevant for their customers, still be able to serve the customers. The extreme behavior customers scenario that I explained in the beginning, the initial context that I gave, it was that we were trying our best to be there. Sales demand forecasts, availability solutions, all of these they were being shared continuously. And this one, which is the identification of stockpilers, was a separate analysis that we actually did, because a lot of retailers were really interested in finding out if these customers are actually behaving consistently, or if there is this certain percentage of customers who are actually not behaving like everyone else. If that is so, can we identify them? Can we do something about that? And that's when we moved forward and we said, let's identify these stockpilers. Let's see how they are performing across regions. Let's see if these are certain kinds of families that we can really focus on. Are these perpetual ones? Are these seasonal ones? Stuff like that. So these are two different analyses, rather questions that we were trying to answer. I hope I was able to kind of answer the question.
Absolutely, yeah, definitely. It was a very, very unique time, wasn't it, for everybody?
Yeah.
And I'd imagine retailers obviously struggled to cope. So having the team at dunnhumby behind the scenes, looking at all the data, trying to help them understand, must have been super, super valuable. Just one comment in the chat there from Jeffrey Payne. Like everyone else, actually, Jeffrey was very impressed, and he's actually said he must watch this again. We are very lucky that all of the sessions have been recorded, so if it is a session that you'd like to watch back, you can. There's a small charge to watch it back, just to pay for the platform, or alternatively, we do give out voucher codes for anyone that gives us a social share. So obviously, as a community, we're keen to expand, we're keen to have as many people watch as possible. So those are your two options. If you would like to watch the videos for free, just give us a little shout out on LinkedIn or Twitter or whatever, and you'll get a code to be able to watch them back. So again, Amir has fired in quite a few questions. Actually, I normally try and avoid loads of questions from the same people, but they look to be very good questions. So we'll keep going if that's okay, Anushree.
Yep.
The next question there at the top, did you experiment with minority oversampling techniques for this particular problem?
To be honest, thank you again, Amir, but no, we did not. I think the discussion, when it really began for identifying stockpilers, we knew everything was quite extreme. We knew we will have to come up with something which has not been tried before, and we knew things can go wrong as well. So we really wanted to find out something that can identify such extreme trends, such sudden trends rather. Even if you plot it on a time series, as a time series data, you'll see that trends were all explosive at that time. So we really wanted to go ahead with something which can really identify these extreme ones, and that's when we decided to really focus on anomaly detection instead. We knew we wanted something which is unsupervised, not supervised, because there will be certain percentage of customers only. We did not want to get into imbalanced data sets, stuff like that. Those discussions were quite, kept aside. They were parked for later because we did not have much time as well. Things were really fast. So I think that's why we went ahead and chose anomaly detection instead. It was easier.
Perfect. That sounds like a very good reason. I'll jump down to a couple of questions there. We'll pick up the questions from Dominic and also from Charlie. And then depending on time, we'll maybe jump back up towards the top. So of those two questions, Anushree, Dominic and Charlie, do you have a preference? Which one we pick up first?
Just go ahead. That's okay.
I love the calls. Just fire them at me. Just keep them coming, Dave. Keep them coming. We'll take the one from Dominic then, first of all. Dominic's asking, in the graph showing anomalies, e.g. you labelled when x1 equals 10, y equals 10 as an anomaly. Wouldn't this be classed as normal behaviour in this case? Because pre and post pandemic, they were behaving in the same way.
Absolutely. Absolutely. Again, I think if you do get a hand on the presentation itself, you'll get to see the charts again. But I did make sure that the scales were the same so that we know what's really happening in the post and the pre-period. But if you can recall when I said that this was the average behavior, this was kind of a rectangle, not a square. So if you think of it, the 10 and the 10 on the pre and the post period axis kind of showed that the post period 10 was quite close because there was the behavior was so explosive there on the post period y-axis. Is the most difficult way that I've actually explained a chart like this, Dave. If you would recall, it was a rectangle there, not a square, and we tried keeping it that way so that we can show the difference between the post and the pre-period.
Perfect. Thank you very much, Anushree. And thanks for the question as well, Dominic. We will jump on to the question there from Charlie. Charlie, like many other people, kicks off by saying, great presentation and really well explained. Thank you, Anushree. When it comes to using the surrogate decision tree to draw out the explanations behind anomaly decisions, does any dependence between the independent variables cause an issue here?
I don't think so. Thank you for the question, Charlie. That's a very, very intelligent question. But I'd just say, let's keep the purpose of building that surrogate decision tree in mind here. Decision tree in itself has a lot of drawbacks, and we did go through that while we were going through the presentation itself. But the purpose here was not to predict anything. It was to interpret the results of iForests. It's fine if it overfits. It's fine that we're building just one tree, not a forest out of it, just to interpret. But we wanted the decision tree to be able to break down the results of iForests. So it's fine, even if things were not independent, because at the end of the day, we really wanted to be able to find those split values, that feature that iForests used in order to find those anomalous and non-anomalous customers.
Perfect. Thank you very much, Anushree. I'm a little conscious of time. There's two more questions. We do try to normally keep these sessions to an hour. Is it okay if we quickly fire through the last two? Anushree, we'll run over a little bit. Just before I get to those, I am going to have to get back into this chat as well, because there's 30 more unread messages that I've not gotten through. So as I did mention, Daniele had been in. He's put excellent presentation and content. Big up, Anushree. Amazing session. Clap, 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 clap. Vipul, brilliant. John, really interesting. A lot to take in. I'd agree with that, John. Arnab, great session. Thanks for sharing it. So Marco, Francis, Dominic, Argi, Anupama, Alan, Lewis, Sashwat, all jumping in, saying how much they've enjoyed it. And actually, I'm pretty sure I've still got another 20 unread messages to get through there. So maybe I'll even try and download these, Anushree, and I'll send them across to you, and you can share with everyone at dunnhumby to show what a good job you've done. In terms of these two final questions, first one at the top there. What methods do you recommend for interpretability for random forest?
Again, thank you for the question, Amir. He's sending all of those questions that are
yeah.
really making me think. Really good questions, Amir. I think, again, the purpose is very, very important. Here, when we were trying to interpret the results of isolation forests, we knew we really wanted those decision rules, the feature that isolation forests use, and hence we used decision trees. When it comes to interpretation of random forests, there are a zillion ways that you can actually do that. But again, the business context itself as to why you're trying to, what is it that you're trying to get out of it? You can still get decision rules out of random forest itself, and there are ways to do that. But I'll always say focus on the problem statement itself whenever you're trying to do or use any other technique for interpretation.
Perfect. Thanks, Anushree. And then absolute final question, just as we wrap things up. It's quite an interesting one, actually. You've done all this work. You've fed all this information back to the retailers. Did you see any change from the retailers? What action, if any, did the retailers take in regards to stockpilers?
Yeah. Thank you so much for the question. So we put all of this effort and thinking to set up a productionized model that can detect stockpilers on a weekly basis, which we've been using actively as part of other analysis that we do, and as a tracking exercise as well, to guide the client for better actionability across regions. What categories are they focusing on? Also, if the chunk of these customers shift from time to time based on certain promotions, offers, events that the retailers conduct sometimes. We did have to change the features a bit, as now it was supposed to not only be a model that detects COVID-driven stockpilers, but something that can identify an extreme behavior on a continuous basis, even normal circumstances. So yeah, this has been a huge development from our side and a big value addition to the client as well.
Amazing. Thank you very much. Thank you. We will start to draw things to a close. I'm gonna first of all start by thanking you again, Anushree. Really do value the time you've clearly put into pulling together such a great presentation, and obviously the time giving up your early evening to come and share with us as well, which is great. The other thing that I do just want to reiterate, Anushree did finish there by saying that dunnhumby are hiring. They are without doubt one of the best data science or data organizations out there. We really value dunnhumby as a partner. The content that they come with is always of the top level, and it's really indicative, I think, of the type of work that they're doing in the company. I'll also give a shout out to Rosie Pryor. I know she's been watching along and has jumped in the chat just to say thanks, but definitely thank you for Rosie for making this partnership happen. So really do appreciate Rosie and dunnhumby. Thanks again to you, Anushree. Thank you all for joining us wherever you are in the world. I guess just before we end the session, final thoughts from you, Anushree. How was that for you? Did you enjoy speaking to everyone today?
Oh, I did. I'm still nervous, Dave.
It did not show.
But I think I'm just gonna like end it at something non-technical. Forgive me for this unwanted advice, if you may, but it's coming from my own experience. This is to everyone. Don't be afraid to be vulnerable in this field of data science. If you feel something can work out, trust that hunch. Data is as much about intuition as it is about experience. So yes, just go all out and do it. And yes, feel free to get in touch with me. I'm there on LinkedIn, Medium. I will be happy to connect with you. Hoping to speak to some of you soon. Thank you for your time, and thank you, Dave.
Perfect. What a perfect end, Anushree. So thank you for that, and very wise words to finish it up. So thank you, everyone. It's been great to see you, and we will see you all at events soon. Thank you and goodbye.